Stoichiometry is the area of chemistry that deals with the quantitative relationships between reactants and products in chemical reactions. It is based on the law of conservation of mass, which states that matter is neither created nor destroyed during a chemical reaction. To apply stoichiometry, chemists begin with a balanced chemical equation, where the coefficients represent mole ratios between substances. These mole ratios act as conversion factors, allowing us to calculate how much of one substance is required or produced from a given amount of another. Whether starting with mass, volume of a gas, or number of particles, stoichiometry provides a systematic framework for converting between different chemical quantities using the mole as the central unit. Stoichiometry is essential for understanding real chemical systems and for predicting reaction outcomes. A chemical change occurs when atoms rearrange to form one or more new substances with different chemical compositions and properties. In other words, the original substances are transformed into chemically different substances. For example, when gasoline burns in oxygen, it reacts to produce carbon dioxide and water. Similarly, when iron nails rust, iron reacts with oxygen to form iron oxide. In both cases, the products have different chemical identities from the reactants. Closely related to chemical changes are chemical properties, which describe a substance's ability to undergo chemical change. Examples include corrosiveness, flammability, acidity, and toxicity. These properties can only be observed when the substance participates in a chemical reaction that alters its composition. In contrast, a physical change is a process in which a substance changes its form or physical state but does not change its chemical identity. The composition of the substance remains the same before and after the change. Common examples include melting ice, freezing water, and boiling water. Although the physical state changes from solid to liquid to gas, the substance remains H2O throughout. Physical changes are associated with physical properties, which can be observed or measured without altering the substance's chemical composition. Examples include color, odor, taste, appearance, melting point, boiling point, and density. Understanding the difference between chemical and physical changes allows us to determine whether a process involves a fundamental change in composition or simply a change in form, which is essential for analyzing reactions and classifying matter in chemistry. Stoichiometry allows us to predict how much product will form from a given amount of reactant and to determine how much reactant is required to produce a desired amount of product. These predictions are based on balanced chemical equations, which provide the mole ratios between reactants and products. In essence, stoichiometry translates the symbolic information in a chemical equation into measurable laboratory quantities such as moles, mass, or volume. Chemical reactions are represented by chemical equations, which show reactants transforming into products. For example, hydrogen gas reacting with hydrogen gas to form H2 illustrates that one hydrogen atom combines with another hydrogen atom to form one hydrogen molecule. More importantly, in stoichiometry, it also implies that 1 mole of hydrogen atoms reacts with 1 mole of hydrogen atoms to produce 1 mole of hydrogen molecules. This emphasizes that chemical equations describe relationships at both the particle level and the mole level. Consider the reaction in which water molecules are formed. The coefficients indicate that 2 moles of hydrogen gas react with 1 mole of oxygen gas to produce 2 moles of liquid water. These numerical relationships are the foundation of stoichiometric calculations. Balancing chemical equations is based on the law of conservation of mass. Atoms are neither created nor destroyed during a chemical reaction. Therefore, the number of each type of atom must be the same on both sides of the equation. An example shown is the combustion of methane, which is initially unbalanced. Before performing any stoichiometric calculation, the equation must be balanced to accurately reflect the conservation of atoms. Only after balancing can we correctly use the mole ratios to calculate quantities of reactants and products. In this way, stoichiometry connects the fundamental principle of mass conservation with practical chemical calculations, making it an essential tool in chemistry. Balancing a chemical equation is a fundamental step in understanding chemical reactions and performing stoichiometric calculations. When chemists describe a chemical reaction, they use a chemical equation to show the substances that react and the substances that are produced. The substances on the left side are called reactants, and the substances on the right side are called products. The first step is to write a skeletal equation, which is simply the unbalanced form of the reaction. In this example, methane reacts with oxygen to produce carbon dioxide and water. At this stage, the equation only shows the correct formulas of the substances involved, but it does not yet reflect the correct number of atoms on each side. To balance the equation, we apply the law of conservation of mass, which states that atoms are neither created nor destroyed in a chemical reaction. Therefore, the number of atoms of each element must be the same on both sides of the equation. A helpful strategy is to begin balancing the element that appears in the fewest chemical formulas on each side. In this reaction, carbon appears only once on each side, so it is already balanced with 1 carbon atom on both sides. Next, we balance hydrogen. There are several important rules to remember when balancing chemical equations. First, coefficients must create equal numbers of each type of atom on both sides of the equation. Second, the final balanced equation should use the smallest possible whole number coefficients. Third, subscripts in chemical formulas must never be changed because subscripts define the identity of a compound. For example, changing H2O to H2O2 or CO2 to CO would represent completely different substances. Instead, we only adjust the coefficients in front of formulas. Changing a coefficient changes the amount of a substance, not its identity. For instance, H2O versus 2. H2O simply means 1 molecule of water versus 2 molecules of water. Methane contains 4 hydrogen atoms, while water contains only 2 hydrogen atoms per molecule. To balance hydrogen, we place a coefficient of 2 in front of H2O so that the product side also contains 4 hydrogen atoms. After balancing hydrogen, we then check oxygen. On the product side, there are 2 oxygen atoms in CO2 and 2 more in the 2 water molecules, for a total of 4 oxygen atoms. To match this, we place a coefficient of 2 in front of O2 on the reactant side. Now both sides contain 1 carbon atom, 4 hydrogen atoms, and 4 oxygen atoms, confirming that the equation is balanced. In summary, balancing chemical equations ensures that chemical reactions obey the conservation of mass and accurately represent the number of atoms involved. This balanced equation then becomes the foundation for stoichiometric calculations. allowing chemists to determine the quantitative relationships between reactants and products in a chemical reaction. This slide continues our discussion of balancing chemical equations with an additional focus on indicating the physical states of substances and understanding the quantitative meaning of coefficients in a balanced equation. When writing a complete chemical equation, we often include symbols that represent the physical state of each substance. These symbols help us understand how the substances exist during the reaction. For example, S indicates a solid, L indicates a liquid, G represents a gas, and AQ refers to an aqueous solution, meaning the substance is dissolved in water. In the example shown, the combustion of methane is written as shown on the slide. Here, all the substances are in the gaseous state, which is typical for combustion reactions at high temperatures. Including these state symbols provides more complete information about the reaction conditions and the physical forms of the reactants and products. This molecular model visualizes the reaction, illustrating that one methane molecule reacts with two oxygen molecules in a combustion reaction to produce one carbon dioxide molecule and two water molecules. Note how the chemical bonds in the reactants are broken and new chemical bonds in the products are formed. Here is another practice example to reinforce the concept of balancing equations. Ammonium nitrate decomposes into nitrogen molecules, oxygen molecules, and water molecules. This equation is not balanced yet. When balancing an equation like this, we again apply the law of conservation of mass, ensuring that the number of atoms of each element is the same on both sides of the equation. Pause the video and identify the four coefficients. The correct coefficients are these. Another important example on this slide is the combustion of octane, a major component of gasoline. The balanced equation is shown on the slide. The equation clearly shows that two molecules of liquid octane react with 25 molecules of oxygen gas to produce 16 molecules of carbon dioxide and 18 molecules of water vapor. The coefficients represent relative amounts of substances involved in the reaction. These amounts can be interpreted either as numbers of molecules or as numbers of moles, which is especially important for stoichiometry calculations. For example, in the combustion of octane, the equation tells us that 16 molecules of carbon dioxide are produced for every 2 molecules of octane burned. Similarly, on the macroscopic scale, 16 moles of CO2 are produced for every 2 moles of octane consumed. This interpretation allows chemists to predict how much product will form from a given amount of reactant, which is one of the central goals of stoichiometry in chemical reactions. Now, let's try an online activity to reinforce our understanding of stoichiometry. Log in to the course site on D2L. Click the Content tab at the top. In the left menu, open Lecture Material, then select the module titled 15 Stoichiometry 1. Under that module, find Lab 15 Stoichiometry 1 and download the lab worksheet. Complete it as you work through the online simulation. Return to D2L and under the same module, open Simulation, Stoichiometry 1. In the simulation, select the Intro window. Select Make Ammonia from the 3 options at the bottom of the simulation page. Set 2 for the stoichiometric coefficient of NH3. Vary the stoichiometric coefficients of N2 and H2 on the left side of the equation until the equation is balanced. Fill in the blank boxes on the lab worksheet. Repeat the same procedure for the separation of water and the combustion of methane. Now click the game icon at the bottom of the page. Select levels 1, 2, and 3 and practice balancing the equations. Fill in the blank boxes in Activity 2 on the lab worksheet.